Okay, let's talk about rolling resistance now. So consider a cylinder, and real objects have some deflection. So this illustrates that they will depress into the surface that they're rolling on a little bit, or they may flatten. If you have a very rigid contact, steel on steel, for example, you'll have almost no deflection on either side, and that will mean the rolling resistance is very low. Train, rolling resistance very low. Nothing can beat a train for hauling things like coal, loads like that. Very heavy loads, very long distances, very energy efficient. The only thing that can beat a train, actually, is a pipeline for liquids and gases. You can't transport coal through a pipeline, but you can transport natural gas or oil through a pipeline. Pipelines are very efficient. Trains are next, but you can't, not everything can go through a pipeline. Rubber flexes a lot. Rubber is like the second situation. So automobile rolling resistance is pretty high. Now a train cannot go up a very steep grade. It's got to go switchbacks a lot to keep the grade low enough so that it can go up it. An automobile, an automobile can go up a 45-degree grade. That's kind of hard to imagine. The Blues Brothers was wrong, where the police cars went slipping backwards on the bridge that was tilted up. Won't happen. The rubber is too sticky. The bridge will raise, the police cars will be stuck there, the policemen will be standing on their brakes for sure, but bridge will lower back down and the police cars won't go sliding backwards. So the Blues Brothers, you guys have seen that 80s movie, it's wrong about that. Now a train would go sliding backwards. So we look at the moment about A. We combine the normal forces on the back side of the wheel with the normal forces on the front side to get a net normal force. The net normal force has to be opposed to the force that is tending to make it go forward, P, the load force, and the weight, W for weight. And it's got to be through the center of mass. So when you add these two vector forces together, you'll have a vector force coming down like this and just equal and opposite to the normal force. But you'll notice the normal force is tending to impede motion. A little bit of x component, positive x component, to impede. And we can look at it very simply using moment equation. W times this A, this is a dimension of some sort, is going to be equal to P times the radius from here to here, times the cosine of theta. That would give this, it's hard to see it. R cosine theta is from here to here. But theta is pretty small, so we can approximate it by PR. Or P equals, let's get a pen up. Come on, there it is. I'll circle this. So to a good approximation, P equals the weight over the radius to overcome friction, to overcome rolling resistance, times A. And this A number is what's called the coefficient of rolling resistance. For railroads, 0.5 millimeter. And of course, the wheels are 300 millimeters. Hardened steel bearings, ball bearings, roller bearings, very, very, very tiny. You don't want bearings to have much rolling resistance. The idea of a bearing is to make the resistance a lot less. Okay, so we move on to an example like this. And we just ask ourselves, this is a curveball again. Now the normal force, the weight down the plane, weight times the sine of 1.2 degrees, and theta is 1.2 degrees. So that weight times that sine gives us that forward motion. That's the P factor from the previous equation. P. We already know P. This will be P. 98 times cosine 1.2 has to be equal to the W, by the way. R, given 100 millimeters. A, we can calculate it. So we're given that this is when it begins to roll. So we ask, what is A? And we can solve that pretty easily. They go through the whole moment equation, but we can go back to the other equation using this as W A. Let's go back 2 equations. WA over R equals P. So R times A equals W times P. There it is. There's the P. Okay. Go back to here. PR equals WA. WA P, that's the force going down the hill, radius. And it's modified a little bit by this cosine. And that's because of this little bit right here. You're thinking about the moment about point A. And that's why they say it, moment about point A. And so we get 2.09 millimeters out of 100 millimeter. Okay, so that is the friction part of the book, and we're done with friction. We will, let's see, what's the next section? I believe it's center of mass. We're going to be talking about center of mass. Yeah, center of gravity, center of mass. So this is a way to find out when you have objects where their expected center of mass is, and you'd have dimensions then. You can calculate the moments, and you can calculate the kind of weights and loads, and all the stuff that we've done so far depends a lot of times on knowing what the center of mass is. That's the next chapter. And then moment of inertia also. We're going to get into that. So with that, end of the friction section.